Good afternoon, everyone. Uh, in this talk, I'll describe our work on self-driving radios, which we believe is a new design paradigm in radio design, where radios come up with their own control algorithms. This is joint work with my colleague Rakesh and our advisor Sachin Kati. This talk is divided into 4 parts. First, I'll go over why we need self-driving radios or SDRs. Then I'll explain what SDRs are. Then I'll go over how to design an SDR through an illustrative example. And finally, I will end with how SDRs perform. This is an apt venue to present this work, as we are celebrating 25 years of mobile computing. We have come a long way over the past few decades, going from digital voice in 2G to mobile web in 3G to mobile broadband in 4G. And today, we are at an inflection point where the 5th generation of mobile networks is envisioned to enable a future connected society, which could range from things like mobile immersive experiences, such as 360-degree video and AR/VR content, all the way to Internet of Things that aims to connect everything in our homes, cities, and even farms, to real-time control for mission-critical applications such as self-driving cars. The same wireless network have to support all these use cases. We have diverse use cases requiring diverse devices operating in diverse wireless environments. This diversity makes the design of a 5G radio a challenging task. Now, before we go into details about 5G, let's look at what designing a radio involves. A radio at a high level involves 2 pieces. First, there's a piece that does the data processing to convert bits to signals that can be transmitted over the air. The second piece is a set of control algorithms that configure and control how this processing is done. For example, the first piece does the modulation, but the second piece decides which modulation order or even which modulation scheme to use in that scenario. Coming back to 5G, the first part, the data processing pipeline, has been formalized in the 5G standard. The standard provides multiple control knobs that, if tuned correctly, can support the diverse use cases of 5G that we saw earlier. However, the control algorithms are not specified in the standard. The focus of this work is in the design of these control algorithms. Let's now first look at how control algorithms are designed today, or in the past in the previous generations of mobile networks. It's a slow and cumbersome process. For every control knob in the data processing pipeline, a human designer does iterative simulations and comes up with a bunch of heuristics based on manual thresholds and trial and error, and finally deploys them in the field. This manual approach is slow and expensive, and hence it's difficult to repeat for every 5G scenario that we saw. This was okay for 4G and earlier generations, where the number of scenarios that radios needed to support was very few. 5G, on the other hand, requires a multitude of scenarios to be supported, and this manual approach is clearly not going to scale. Against this background, to make radios ready for 5G, we propose a self-driving approach to designing control algorithms, where the human radio designer just enumerates a list of high-level design specifications, and then AI takes care of the rest. The design specifications go into a learning engine powered by state-of-the-art AI techniques, which then come up with a neural network-based control algorithm, which is finally deployed in field. This approach is fast and cheap, and hence this can be easily extended to all 5G scenarios. We'll also soon show that this approach is near optimal too. We call this approach self-driving approach, and the radios designed self-driving radios, or SDRs, because the radio drives itself after getting the high-level design specifications from the designer. In doing so, we repurpose the original SDR acronym, which originally stood for software-defined radios, to a more general self-driving radios. Now, let's go deeper into this approach through an illustrative example. I said the radio designers have to just provide the high-level specifications. Let's see what they are. There are 4 of them: the communication objective, the control knobs available for the radio, the measurements available, and a model of the wireless environment. Let's look at an example. Let's say the designer wants to optimize a radio in a mobile phone to meet a throughput target of 3 megabits per second in uplink while minimizing transmit power. This could be a typical scenario in, say, video conferencing, like the case Pan was presenting earlier. So in this case, the objective function might look something like this, where we want to increase throughput and decrease the power consumed. Now, for this case, the radio designer might want to control two control knobs, modulation order and transmit power. Modulation order describes how many bits you pack into a single symbol that you transmit over the air, and hence it directly affects the throughput. Now, this is a hard optimization problem because of the following dilemma. Suppose you want to increase throughput. For that, you increase modulation order. Now, suppose when you increase modulation order to maintain the same communication reliability, you will need to increase transmit power too. But that increase in transmit power will decrease your objective function, which you originally started out to maximize. This makes the problem hard and challenging. Now, the measurements available could be a set of variables representing channel status and optimization status. And the wireless environment model could be any of the standard wireless model used in the wireless community with a defined set of path losses and mobilities. Once the designer specifies these high-level specifications, it goes into our learning engine, which converts them into a control algorithm. I won't go into details of the learning engine here. You can refer to our paper. But basically, what happens is that the learning engine does deep reinforcement learning, specifically deep Q learning, to come up with a neural network that maps the measurements that we saw to control actions. The neural network is trained using a simulator based on the wireless environment model that was specified. Now, this is the architecture of the neural network that we used. Again, I won't go into more details here. The only thing to remember here, at least for this talk, is that channel estimates, which is a proxy for the signal to which is tied to the signal to noise ratio in the channel, is one of the inputs to the neural network. Now, once the neural network has been trained, we get a control algorithm trained for the scenario of a cell phone requiring 3 megabits of throughput. Now, suppose we want to now support connected cars requiring the same 3 megabits throughput. So connected cars have a lower power constraint than cell phones, so we just change the energy sensitivity factor in our objective function and train another agent. That's it. We now get a control algorithm for a connected car requiring 3 Mbps. Now, suppose later you need a similar control algorithm for a connected car requiring 5 megabits of throughput. No problem. We just change the throughput in our objective and then train yet another SDR agent and deploy it. This shows the raw power of the self-driving approach. Flexibility. Designing control algorithms for new scenarios just involves stating the high-level design specifications and training the corresponding SDR learning engine. Now, the natural question to ask is, how well do these perform? Are we sacrificing performance when trying to achieve flexibility? Do the AI-generated algorithms even come close to their human counterparts? To answer those questions, we compare SDR against 3 benchmarks. First, a state-of-the-art modulation order and power control algorithm, which is one of the reference algorithms used in today's LTE networks, and an offline optimal scheme, which is the best any scheme could theoretically achieve. We compute this using dynamic programming, assuming perfect knowledge of the future. Since it assumes perfect knowledge of the future, it's not practically implementable in real life. But still, it gives us an idea of how good any scheme can go. Remember that our objective had 2 components to it. One was to meet a throughput target, and the second was to minimize the power consumed. Let's look at how each of the 3 schemes perform with respect to these 2 metrics. The absolute numbers here don't matter much, but the interesting thing here is that SDR not just comes to today's state-of-the-art algorithms, but is in fact able to outperform it. And even more interesting thing here is that SDR uses a lower average power than today's state-of-the-art algorithms in achieving this better throughput. Now, this was for the case of the phone requiring 3 Mbps. We could see similar gains for the connected car requiring 5 Mbps scenario too. This shows that SDR gives us flexibility without sacrificing performance. In fact, the performance is better than state-of-the-art algorithms. Now, the next natural question to ask is, what is enabling the superior performance of these AI algorithms? To do that, we do what's called a sensitivity analysis, where we fix all but one input to the neural network and sweep that input over its range of possible values and see how the neural network responds in its control actions with respect to that change. We do it for the most recent channel estimate, which I said was one of the inputs to the neural network. We sweep the channel quality from poor to good along the x-axis here and show the transmit power and the modulation order that the algorithm chooses. This is a snapshot for the case of the phone requiring 3 Mbps, and this is a snapshot for the case of the connected car requiring 3 Mbps. Now, stepping back, We would expect a sensible algorithm to use lower transmit powers and higher modulation orders as the channel quality becomes better. We could see that the neural networks have learned to do the same thing from scratch. Now, if we analyzed we did this analysis for multiple variables in different scenarios, and what we concluded was what's enabling SDR to outperform human algorithms is that it's able to adapt the answers to 3 questions on the fly. First, at what channel threshold should the modulation order be switched up, like here? And second, should the transmit power also be switched up simultaneously, and by how much? And third, at what channel threshold should the transmit power be switched down? The answers to these questions vary a lot depending on the scenario in which you are in and the specific use case that you are trying to optimize for. And it's this ability that gives SDR an advantage over state-of-the-art algorithms, which are just basically hard-coded rules. This shows the final feature of the self-driving approach, interpretability. The AI algorithms that SDR comes up with gives us valuable insights into their behavior, and it could also be used to design better handcrafted algorithms too. This interpretability could also increase the confidence of engineers using this approach. Therefore, to conclude, with self-driving radios, we bring AI to the lowest layer of mobile communications. This approach is flexible, near optimal, and interpretable. It's flexible because it's cheap and fast to adapt the 5G radio stack to new scenarios. It's near optimal. It beats state of the art and comes close to the theoretically optimal solution. It's interpretable because the behavior of the agent gives us valuable insights into designing better handcrafted algorithms too. Thank you.